This is video clip 3, topic 10, Introduction to Regression Analysis, Simple Linear Regression. In our previous video clip, we were talking about the use of the scatter plot to help visually understand what regression analysis is all about. And if you look at that series of data in there, you could probably think there's probably a line that best could fit through all these data points that best represents that data. A single line that we could look at that helps us interpret that mass of data points out there. And again, this is kind of a simple version of it. Obviously, you're going to have some outliers. You might have someone who's relatively young that has high costs for a variety of reasons. Obviously, you might have some people who are a little bit more advanced in years that have lower costs. Understanding that there are going to be outliers. But again, we're trying to understand the procedure more at a conceptual level. So we're going to kind of present a more of a simplified example. Now, if you use the, if you take a look at the scatter plot, you can also envision the fact that there are two standard normal distributions involved here. The standard normal distribution of the X data, the age data. There's a distribution of ages centered around the mean with frequencies given standard deviations around that mean. Okay, so in order to keep the scatter plot neat, I'm going to do an upside down bell curve. Okay, so normally we'll have a bell curve that looks like this, right? And it's going to have asymptotes at the end. It's going to be bell shaped, most of the data points around the mean, and then less frequencies of data points as one starts to move from the mean. That's just the standard normal bell curve that we talked about in an earlier presentation. Well, let's do it upside down just to keep it out of our data. We'll take this X data, not even thinking about the Y data. Just hold the Y data in abeyance for a while. Don't even think about it, but there's a distribution just of the X data per se. And obviously there's a mean in our sample that's denoted by X bar for the mean. And in the population we denote it by mu. We might even call it mu sub X to indicate that it belongs to the X data that's in the population to which we're inferring. And obviously around these means, around this mean, we have standard deviations. S sub X, let's use the statistics just to keep it simple. S sub X negative, S sub X positive. Now the drawing isn't going to be perfect, but you just remember from the earlier discussion of data distributions that most of our data points in terms of the absolute maximum amount will fall on the mean of the distribution, and then as you start to move away from the mean, as you start to move into more and more standard deviations from the mean, there are going to be fewer frequencies of data points. Anyway, that's just our standard normal distribution of the X data, which is defined most precisely by the X bar, the mean of the distribution. Concomitantly, there's a distribution of Y data on a standard normal bell curve also. And again, we'll put it sideways because it's got to fit with that Y-axis. So the healthcare cost data also in the population that we're estimating fall around a standard normal distribution of healthcare costs across this age range. And in the very peak of that distribution, we're going to have Y bar, the mean of the healthcare cost data. And then again, you're going to have negative S sub Y. It looks like an X, but it should be a Y. So you're going to have standard deviation units up and down this also. So 1, 2, and 3 standard deviations around Y bar, 1, 2, and 3 standard deviations below Y bar. So again, you've got two distributions, and these are called marginal distributions when we talk about regression analysis. Marginal meaning that they're at the margins of the scatter plot. They don't take into account the other data set. When looking at the X data set, you just look at the standard normal distribution of ages in our sample that we're using to infer to the population. Likewise, in the healthcare cost data set, we're just looking with the marginal distribution, we're looking at the distribution of healthcare costs given this age range with this defined by a mean and standard deviations with a standard normal distribution of scores. Now if you start looking, if there's a relationship between these two data, which visually we can see that there is, it seems to be direct, a fairly strong direct relationship between age and healthcare costs. As we start to ascertain that there's a relationship between X and Y, we can start talking about conditional distributions. Well, we can use conditional distributions whether there's a relationship or not. But as there's no relationship, the conditional distribution is going to equal the marginal distribution. But we can talk about tighter distributions if we start looking at distributions around a certain data point. Let's say in this case, for example, that the mean of our age range is 40 years old, just to throw a number out there. Let's say the mean equals, X bar equals 40. That's an assumption. Well, let's then go at, let's pick a certain data point, say X equals 45. And let's say X equals 45 falls right about here. This is age 45, right, along that dot. We can continue this line up in the distribution, and what we can find is a distribution of the Y data contingent on X being set at 45 years of age. So we also have a distribution within the data set defined at X equals 45. And I probably didn't draw that distribution all that great, but we'll leave it as it is. So this is called a conditional distribution. Conditional distribution of Y, because we're looking at the Y distribution here fixed at a certain level of X. So that conditional distribution, if there's a relationship, will be smaller than the marginal distribution, because using the relationship between X and Y, we have we've reduced the error in Y, what we know about Y. So the conditional distribution is actually going to be smaller than the marginal distribution, if that makes any sense. And at the conditional distribution, we have a certain predicted mean score, predicted in the population in the sample. This is actually a known value. At X equals 45, we can actually calculate a very precise mean of Y just for subjects who are at age 45. And we denote this mean value of the Y distribution that's part of the conditional distribution as Y hat. So that's a predicted value, Y hat at X equals 45, or any value up and down the distribution of X scores. So if we take a whole bunch of conditional distributions, we have a series of Y hats. As you can see, because of the scatter plot, because of the orientation of our data, the Y hats tend to increase as you move up. As X increases, the Y hats tend to increase as well, because we seem to have a direct relationship here. Now, if you take a line and connect all of these Y hats, this line would run through all of the Y hats, you would have what's called the regression line. And the regression line is simply a line that fits through all of the conditional distribution means, all of the predicted values of Y. So at age 45, the predicted healthcare cost at age 45 will be this predicted value. Y hat means predicted, but it's also the mean of the conditional distribution. And the regression line is considered the line of best fit for the Y data given what we know about the X data. And this regression line is going to be used as part of the regression analysis. So hopefully that's making some sense. As there is a tighter relationship between the two, we have a higher degree of predictability of those Y data. And we'll talk about standard errors of the estimate during the next video presentation, because that's also a part of it, is how tight these data points are. And as we have no relationship between X and Y, basically our conditional distributions are going to equal our marginal distributions. We have no predictive power if there's no relationship. Obviously, if you're trying to relate two variables that are totally unrelated, you can't predict Y based on X. That's all error. And you might as well just have the data points and choose at random. But again, we can draw a regression line, and this is what regression does. It actually calculates this regression line, and that is the line that describes, as a single line, best describes our data. And this regression line then is used to calculate some of the regression statistics that are used as part of regression analysis. So we'll go ahead and continue the discussion, given this visual graphic description of what regression analysis is really all about. We'll go ahead and continue the discussion during the next video clip.